Thanks for the invitation from the organizer, and my name is Jun-Yan, and I'm currently a research scientist at Adobe, and I'm also incoming professor at CMU. So thanks for coming to my talk, and today I would like to talk about our recent work on visualizing and understanding GANs. So every month there are lots of GANs papers for image generation, image editing tasks. Including lots of exciting progress and new applications, including models with higher and higher resolutions, such as these progressive GAN papers. However, some researchers in computer vision and computer graphics are still hesitant about this family of models. It's a black box. You train the black box. You pray for the GPU god. Most of the time it's great. Sometimes you get bad results. So it's hard to understand why it works, why it doesn't work. Um, so here we try to take our first step to understand what's inside the model and shine some light into this black box. So we take a standard GAN model, progressive GAN by Karras et al. So this model learns to generate random images for a specific category, such as outdoor church. But what is this model doing? Does it just memorize every single image in the network, or does it learn something interesting? So let's take a close look. So this model takes a random code as input and applies a few convolutional layers. So each layer gradually increases the spatial resolution of the input, and eventually you get a high resolution RGB output. Well, this gigantic network is highly nonlinear as there are lots of layers. In this work, we try to see what the system is doing if we take away parts of it. So here we focus on a particular layer which consists of a set of neurons. Here we try to examine a particular neuron and its feature map, which encodes how this neuron fires on the input data from the previous layer. We want to know what this neuron represents. So we take a very simple approach. We can first generate an image by sampling a random code. And we also look at the feature map of that particular neuron and that particular layer. And we record the high response region, which is above a certain threshold. And now we can compare this binary map with the output of a semantic segmentation model, which segments different objects given the generated image. So we want to check if this neuron correlates to a sky concept. In this case, probably not. Does it capture a building concept? Probably not. Is it correlated to a tree concept? Yes, in this case, the semantic segmentation map aligns pretty well with this binary threshold map. So we can calculate the agreement between these two over many images, and we'll do it for all the neurons and all the object categories we have. So here is what we have found. So our first surprise is that in this model, lots of neurons match object concepts. It's quite interesting because during the training time, we have never told the model what a tree is. So the model was only told to generate outdoor church. But along the way, the model discovered the tree concept internally. A second surprise is that these neurons seem to match objects with a wide range of visual diversity, like different lighting, different materials, at different locations. So we can look at a different model trained for generating dining rooms. So there are a window neuron and a table neuron. And I'm not just cherry picking these two examples. Actually, in this particular layer, layer 4 of the progressive GANs, 250 out of 500 neurons are correlated to the concepts of objects, object parts, and materials. For example, there are kind of almost 20 window neurons in this layer. And we can further zoom out and see all the layers. So in this diagram, the model starts from the latent code at left and the output pixels at right. So the height of each bar shows the number of concepts at that layer. So in the first few layers, we see some global layout structure. In the middle layers, we discover many neurons that correspond to objects and object parts. In the later layers, which are very close to the output pixels, we find neurons that capture low-level structures such as long edges and textures and details about the image. But so far, we only measure the correlations. A neuron might correlate to an object's concept somehow, but may not cause the object. So here we try to study causality. Again, we run the generator, but this time we force the neuron to be completely off. And we generate an image with fewer tree pixels. We can force the same neuron to be completely on. And we get an image with more tree pixels, with lots of tree pixels indeed. We can calculate the difference between these two images regarding the number of tree pixels, which is the average causal effect regarding this neuron. So once we discover these causal neurons, they are not only correlated to a tree concept, but now you can remove trees from a particular image by turning these neurons off. Or you can add trees by turning them on at particular locations. So we can use this technique to study object-scene relationships. For example, we can try to remove people from a conference image, and they get removed. We can try to remove windows. Most of the windows are gone, and some of them become paintings. But while we try to remove a table, the network refuses to do it. It only shrinks the table because the table is quite essential for a conference room. We'll do the same thing to chairs. In this case, chairs are still there, but the number of chairs decreases. So we can quantify this phenomenon over many images. This can help us understand which objects are essential for conference rooms. Similarly, we can also insert objects into the scene. So this yellow bounding box highlights the most likely location where you can insert a door on a church. For example, you can insert a door to the building, but you cannot do that into the sky. You cannot insert a door into the sky. Here is another example. Here is a quantitative evaluation, which says that you can turn a window into a door, you can add a door on the buildings, but the model refuses to add doors to trees and skies. Why is that? Because this will break the notion of the realism captured by the model. So adding a door on the sky will make things look unrealistic, and the generative model has captured that. We can also understand artifacts by looking at these kind of internal neurons. So here are image with lots of artifacts. So sometimes you might get some bad results like this, and you may ask why. What caused these artifacts? In this model, the bedroom model of progressive GAN models, we find there are several nasty neurons which consistently generate images with artifacts over and over. Once we locate these neurons, we can now turn off these artifacts causing neurons, and the results become much better now. So based on the insights we have learned, we have open sourced an online interface where a user can control the internal representation of a generating model. So here you can add a dome, you can paint a tree, you can draw the sky. If you don't like some objects, you can just remove them. We have remove button. You can remove the grass, but removing the grass does not create like a black hole or white hole. It actually hallucinates a new street and sidewalk. The program is quite intelligent. It allows the user to add a door on a building, but if you try to add a door in the sky, the model refuses to follow your instruction because again it doesn't look realistic, and the model has captured that. So far we can manipulate and generate images, but how can we use this tool to edit a user's own photo, a photo taken by a camera? Because oftentimes you don't care about generated images. They are generated by the model. You would really like to manipulate a photo that you are taking, a family photo or a portrait. You like to do some editing. So here is a real image of a kitchen. So to edit a real photo, the first step is to find the latent code that can reconstruct the image. And this allows us to do everything in the language of GANs rather than doing everything in the language of pixels. In 2016, we proposed a simple method called IGAN for achieving it. The objective is to minimize the distance between the generated image and the original image. So this is the original image I, this is the generating models with model parameter theta, and we try to find a z which can minimize the distance between these two. So this distance can be like a very simple L2 distance. It can also be a more like sophisticated distance, like this perceptual distance. And so you can do it with great descent, but oftentimes it helps if you actually train a model to predict the z, train a kind of encoder model to predict the z, and use that as an initialization. And here is the reconstruction results. It's not bad, but it roughly reproduced the appearance of input. But if you look at these two images closely, there are many differences. So let's try to find them. What is the difference? You still have a kitchen, but you have no microwave, you have no chairs, you have no stove. The kitchen is perhaps not very usable. So in February of 2018, we present a new method. So instead of optimizing the z alone, this time we try to optimize both the latent vector z and the network parameter theta. So we try to modify both of them so that you can generate an image which are closer to the input. Of course, if you modify the network too much, it will start overfitting and lose the original structure learned from the data. So therefore, we add a regularizor that enforces the new model to stay close to the original model. And here is the result. And we can do a side-by-side comparison. This is with latent code alone, and this is when you're optimizing both the latent code and the generating model. And this idea is largely inspired by the work such as deep image prior and deep internal learning. So the idea is you try to train a model just for a single image, and that model only works for that image, but that's you have already achieved your purpose. You want to have a method that works for a particular image. So with this new reconstructing method, we can also produce much better edits. So here is the original one. Here is we try to insert a window. So we actually inserted the window, but all the details are missing. So here is the method which we insert the window, but also keep all the rest of the details in the image. I think what's really fascinating about GANs is that you can actually see this kind of reflection on the here and created by the window. So it's not only adding a window pixels, but actually try to affect its surrounding, which is quite interesting and not possible by traditional methods. Here's another result where we can remove the chairs. Here's another result. Again, we can add a window here. Here we can edit the tree, and we can actually, by activating different neurons, we can generate trees with different styles. So here's a demo of how we edit an outdoor image. So far we only look at what kind of images a GAN can generate, what kind of concepts a GAN has learned, and we use this kind of idea to build this kind of smart editing tools. But there are the other side of other aspect of the story, which is what a GAN cannot generate, which is the weakness of the GAN, and we try to answer this question in the next chapter. So let's revisit the current way to benchmark a GAN. First, you generate a bunch of images using the model. You also collect a bunch of real images, and you feed both images into an inception network. And then you can calculate the features for each image, and then you can collect the feature statistics for both fake and real images. And then you can calculate the difference regarding this kind of statistics. A popular choice could be FID, but what FID is doing is it try to measure the amount of error to give you a single number, but doesn't tell you what is wrong or what is missing. Now we'll also look at the current way to see or visualize a GAN's capacity. Usually people will have some FID tables. They also have some figures which shows a bunch of generate images, like for them 4x2 like generate images might be a good choice for a figure. And again, it's just visualize what a model can generate, but you don't know which images it cannot generate. It never knows. So we try to understand the question of what a model cannot generate, which is also kind of what kind of modes the model has dropped. We try to answer this question in the distribution level, which will try to on average what kind of stuff the model is not able to generate. We also try to look at individual image level for each particular object for a particular image, what is missing from the GAN's perspective. So let's try to answer the first question. What is missing in the distribution level. So here we propose a very simple method. Again, we take a real image, we segment it, we take some another real image, we segment it, so we can calculate the statistics of the different semantic categories for real images. We can do the same thing for the fake images and we'll compare the difference. So here we show this is kind of the percentage of the pixels for each semantic category. Like this is like bad pixels, how many bad pixels, how many floor pixels, how many window pixels. So the blue bar is the statistics we get from the real training images, and it's this red curve. This red curve is the same statistics we get from the generated images, and this is in the log scale. And here we try to calculate the difference between this red curve and the blue bars, and we can magnify it and to see it. For example, we over-generate the building and sky, but we cannot generate person. We can look at this kind of statistics for different models. Here is the baseline model used in the style GAN and train on the same dataset like Elson bedrooms. And we can see that for the baseline, we can see there are large deviations, and for a better model like style GAN, we can see a much smaller difference between this kind of semantic statistics for the real and fake images. And we can also visualize what particular category is missing. So again, we can see for the outdoor images, lots of persons are missing. We cannot generate cars, we cannot generate fans. So this plot is quite informative, but it only shows the general trend of the entire dataset or the entire distribution. Dataset. We'll also try to focus on a particular image and see how this model behaves for a particular instance. So here we use this idea of kind of image projection, image reconstruction. We try to generate an image using a GAN model, and here is an image actually generated by the GAN model, and we can try to invert it. Basically, we take this image and try to kind of guess what Z is used in the first step. And actually, for the generated image, we can perfectly, precisely reconstruct this image. But it's not the case for a real photo. So here is a real image. We run the same optimization pipeline on this real image. We try to reconstruct this image, and we get these results. It's not the same anymore. And note that in this case, we only optimize a latent feature Z, and we're not optimizing the generator because we actually try to study this particular generator's capacity, so we don't want to change it. And this Z can be the input latent vector. It can also be some intermediate feature layers. So oftentimes it works better. The construction works better if you try to invert a particular intermediate feature layer. And now we can see what again cannot generate for a particular image. So here is the original photo, and here is the reconstruction from the GAN. And here's another one. Maybe you feed a kind of wedding photo to this method, and here is the one. So the building is still there, but that couple kind of missing. And we can see more results. Again, the general trend through this visualization is this GAN model can kind of generate the building and the environment pretty well, but it always tend to ignore the persons. So there's some difference, because maybe you can argue that maybe it can generate a person, but the quality is bad. But in this case, it's not that case. it actually cannot generate a person. It just ignore the person completely. And here is more example just show to skip the persons. And also skipping the vehicles or the cars, like buses, they are gone. It's also interestingly try to skip this kind of signboard and all kinds of like the text, different text. Also try to ignore the monuments. So my hypothesis is that there are only like a few percent, like 5% of pixels, which actually are about the persons, like pedestrians, about vehicles, about the monuments. So even if you ignore these 5% of pixels, if you measure FID, it's still okay. It's not a zero FID, but you can achieve a very small FID by ignoring these kind of rare categories, like non-important categories. If you can actually generate 95% of pixels. Again, the GAN model can generate the entire building, but sometimes ignore some architectural details. We can use the same idea for the bedroom models, and a lot of details are missing. Like these very sophisticated patterns, you cannot generate that pattern from using a GAN model. Or like these kind of wrinkles, it's very hard to generate. You may think this image looks okay, but until you see the original photo, they are still very far from actually generating a realistic photo with all the details, like wrinkles, like these kind of the photos on the wall. It's still very far from there. And more interestingly, if you feed an image which are not exactly the bedroom, it will actually hallucinate the bed. In conclusion, this kind of reconstruction tool can allow us to see the world as the GAN can generate. And a lot of these details are missing, and we are still very far from the goal of just recreating all the visual experience, the richness of the visual world. And these details might not matter in terms of FID, it might matter maybe affect like 0.1 FID, 0.05 FID, but this kind of all these wrinkles or on the bed or this wallpapers pattern, they matter for humans' eyes. And I believe it also matters for like this workshop, like people synthesis, because you will see all the wrinkles on the clothing and all the details of the humans, and people are really sensitive about that. But maybe they are not reflected by the FID. So FID only has captured the majority of pixels, but all the details may not matter. But we still try to fix them. And by that, I want to thank my collaborators, especially the leading also David, who did most of the work, which I have presented. And thank you for your attention, and feel free to try our code and the demos. Thank you.